Good afternoon, everybody. I hope you can hear me well, you can see me well. I would like to welcome you at our today's ATENA webinar, which will be devoted to modeling of bridges and their long-term structural performance. I still see that few more people are joining us. So meanwhile, I will start sharing my screen and set some general information about our webinar. So I hope you can see my screen now. Hope you can see the presentation. And before we get started, I would like to announce that the webinar will be recorded. So everything you want to know, and if there is anything you want to get back to, you can later find it on our YouTube channel. To set some ground rules for those of you who join our webinars on regular basis, you probably know how it goes. We will show some information about ATENA, and if you have any questions, I recommend you to type them into the chat box, and once a while I will stop my talk and go to see the chat box and answer your questions. Maybe if I can ask you to have your microphones turned off at the beginning, so there is no disruption, and maybe at the end we can have some discussion, and we can all talk. So let's get started, so we have time to cover everything we plan. Today's topic is modeling of reinforcement corrosion of existing bridges using the ATENA software. So mainly I would be talking about our recent advancements in modeling of long-term degradation mechanisms using ATENA. It's not the work I do. It's also big collaboration with my colleagues here in Cervenka Consulting. And I will start with some basic and brief overview of modeling of reinforced concrete bridges using ATENA. I will focus on reinforcement modeling and on some specific topics related to bridges, mainly give you some overview what are the possibilities of modeling prestressing elements. And then I will move to the second part of the presentation and second part of our webinar, which is devoted to reinforcement corrosion and long-term degradation. I will give you some quick theory, and then mainly focus on the pre-processing using the GID software and data post-processing in ATENA Studio. Finally, I would like to show some examples of this application and how can we evaluate the structural performance with respect to valid codes, mainly the FIB model code. So let's get started and with a brief overview of bridge modeling using ATENA. For those of you familiar with the software, you know that there are many different elements and different materials which are suitable for this topic. Here I try to somehow summarize them on this slide. Probably most of you are familiar with the basic elements, which are actually the best suited for simulating complex stress conditions, which may occur in many concrete structures, as well as in bridges. When we are talking about bridges, this might be some region around the supports, some regions with some strengthening inside of a bridge segment. Here this points to the shear region where complex stress rate can develop, and which may result in cracking here. If the structure behavior is clear, if it's not so complex, and you want to save some computational time, you can use some simplified elements included in ATENA. Those are mainly the shell and beam elements. Furthermore, for the substructure, which is in this case not the main interest of the analysis, we can use linear elastic elements, etc. Furthermore, if we have a segmental bridge like this and want to simulate the potential slip between the segments, for this purpose, there are contact elements or interface elements, if you want, and for all of them, excluding the linear elastic elements, we can simulate the nonlinear behavior. This can be also done for the steel reinforcement, shown in here. ATENA supports both discrete elements and smeared reinforcement elements. One of the main advantages, from my point of view, of the discrete reinforcement is that that they are automatically connected to the rest of the solid body, so you don't need to worry about some manual definition of the fixed contact between the discrete bars and the concrete, but ATENA does it for you automatically. Furthermore, for the discrete reinforcement, we can apply a bond slip law, which typically for when we are dealing with a large bridge structure where the finite elements are in order of centimeters or decimeters. This is useful for capturing the potential slip between the reinforcement bar and the surrounding concrete. If you are focusing on some smaller analysis, for example, if you are a university researcher trying to reproduce a laboratory experiment on some small sample, this bond slip law is maybe not necessary, because if the elements are sufficiently small, the slip of the reinforcement bar can be captured by the cracking of the surrounding concrete. If you are more interested in this topic, we have 2 or 3 webinars available on our YouTube channel, which specifically focus on modeling of reinforcement, and there is some special section even devoted to modeling of the typical pull-out test in the laboratory. Then when we are dealing with bridges, we often want to apply prestressing. This can be in a form of bonded and unbonded cables, meaning that we can simulate the prestressing, which is done either in some factory or on the site. This is simulated with very similar elements as the discrete reinforcement. However, we have some special material which can even simulate which can simulate the prestressing losses, which is a typical phenomenon from this type of technology. Both discrete reinforcement, smeared reinforcement, and prestressing tendons can capture the material nonlinearity, meaning that after we exceed the yielding strength of the material, we simulate the yielding up to the ultimate elongation, and then we can simulate the rupture of the bar. One more note to the bond slip models available in ATENA, which can be applied for the reinforcement. This means that in ATENA, if we want to simulate the discontinuity between the bar and the concrete, we add one additional degree of freedom to the reinforcement. This degree of freedom has a special material law corresponding to the bond slip and bond strength function. And as the stress in the interface between the bar and the concrete increases, we can simulate that different value of stress is transferred through the interface. When you preprocess your problem in ATENA using the GID preprocessor, there is a tool which allows for automatic generation of the bond slip material law. I mean that based on the strength of the concrete and type of bars and the bond quality as defined in the FIB code, it automatically generates for you the bond slip function. Currently, there are available three different libraries or the bond slip law according to three different studies. Two of them are the FIB model code. Based on this, basically what the tool does is that it generates generates the bond slip function. It gives the maximum bond stress at the interface, and it defines you need to only define the remaining parameter, which is the perimeter of the reinforcement bar. Furthermore, in this option, you can define whether you fix or not fix the ends of the reinforcement bar. This typically, if it's reinforcement, can be set as that the both ends of the reinforcement are free to slip. However, if you are dealing with some design in some let's say earthquake prone regions, there is often used design where the ends of the bars have the end hooks to better connect with the concrete. So if in your global model you don't want to specifically model this kind of region, you can use this option and set that the end of the bar is fixed, either the start or the end or both ends, and this can efficiently simulate the end hooks. If I move on and just again remind you that there is a special webinar devoted to modeling prestressing, but since we are dealing with bridges, I was thinking that it's a good idea to give you some quick overview of the possibilities. So if we are modeling prestressing, we have basically two options in ATENA. Either we prescribe the prestressing as the initial strain, which is applied to the model, and the resulting forces are transferred to the concrete. In this case, it kind of corresponds to the situation when the prestressed element is casted in a factory. For example, the case where we first use the cables, we stretch them, then we cast the concrete, and then we release the prestressing, and what happens is that the stress, the prestressing a little bit relaxes due to the elastic shortening of the concrete. So this is included in this method, and or the other option is that we prescribe the directly the prestressing stress. This is again more similar to the construction when we, for example, create a segmental bridge where we use the hydraulic jack to prestress the cables, and in this case we directly prescribe the stress as it is on site. For this is implemented in the material model called cable and internal cable, which have one slight difference. The cable is meant that it's connected with the concrete at some discrete points called deviators, and it can even account for the prestressing losses that occur in the deviators. The other cable is the internal cable, which is meant that it's placed in some duct, and in this duct it can account for the prestressing losses due to the friction between the cable and the duct. This is automatically calculated in ATENA, and you can even simulate the phase when the prestressing is applied, and then again the phase when the duct is filled with some mortar, and from this point the cable cannot slip and is connected to the concrete with the material of some given strength, which corresponds to the mortar in the duct. When we define the reinforcement, there are and especially the bond of the reinforcement, there are three more options. One is that we can use a function which is relative for the bond strength and can account for the reduction of the bond strength due to temperature. And similarly, we can set the function of the bond strength as a function of corrosion and also as a function of location dependency if we want to simulate that at some part of the cable the bond is not as good as at the remaining part. Today I will mainly deal with this corrosion dependency, which I will show you how ATENA can automatically calculate the chloride ingress and chloride-induced reinforcement corrosion, and based on this corrosion of the reinforcement bar, the bond strength can be adjusted automatically in your analysis. So where this all leads to is the application of ATENA for accessing the long-term structural performance, or if you want, we can call it a development of the digital twin of the real structure, which is then possible to use for aging management of the structure, and to deduce how the performance may be affected by degradation mechanism. So basically, we are moving from evaluating this short-term behavior, as it can be either from static or dynamic or cycling loads, to the long-term performance. And in ATENA, Basically, these four mechanisms are already implemented as the long-term degradation mechanisms, and it's the chloride attack and carbonation, which both results in reinforcement corrosion. And furthermore, there you can account for the cape and shrinkage, and also for the alkali silica reaction and subsequent degradation of the material performance and of course structural performance. So now today I would focus on this first part, which is the chloride attack and how it results in reinforcement corrosion. So this will be the brief overview of the approach used in ATENA. So if we want to develop a digital twin for accessing the durability and long-term structural performance of a bridge, we basically start with a similar model as for the static behavior. This is the finite element mechanical model, which as the main outcomes give the stress and strain distribution over the structure and can be used for accessing the load-bearing capacity. Furthermore, as we are dealing with nonlinear modeling, in ATENA you get the crack width distribution over your model. So this part is calculated in the mechanical model, which is then coupled with a mechanochemical model. In case of the chloride attack or chloride-induced reinforcement corrosion, it is designed that we first calculate the chloride diffusion through the material. This is simulated as a simple diffusion model, mainly governed by the chloride concentration at the surface, the diffusion coefficient for the chloride, which is in this case a time dependent material properties, which accounts for the diffusion and also for the binding of the chlorides to the concrete, and it's accelerated by in the presence of mechanical cracks. This is this term. This is represented with this term in the equation. And based on this, we can calculate the chloride concentration at given depth under the surface at given time. If this chloride concentration exceeds some critical value, we call that this is the end of the induction phase, and ATENA starts to calculate the reinforcement corrosion. The reinforcement corrosion is calculated as the depth in which the corrosion zone progress in the cross section of a reinforcement bar, and it's a function of temperature, of mainly the temperature, the chloride content, and the corrosion time. One feature of this approach, which is beneficial for the numerical calculation and for engineering application, is that of course the mechanical model is in full 3D. However, to speed up the calculation, the chloride ingress, the chloride diffusion, is assumed as a 1D problem only under the surfaces which are in contact with some chloride content. Therefore, we don't need to calculate the full 3D diffusion problem, but can simplify it as a 1D model and speed up the analysis. So in this figure, you can see some representation or some outcome from the analysis for a simple L-shaped beam. So assume that there is a uniform chloride load at the bottom surface. However, due to the mechanical loads, the mechanical cracks developed in this segment. Then, when the chloride diffusion is computed, the chloride penetration in the region with the crack is accelerated, which results in higher reinforcement corrosion in this region. This is shown by this 1D plot along the bar, compared to this region where we see no reinforcement corrosion, while the chloride surface content was the same. However, there were no mechanical cracks. In case of reinforced concrete bridges, this slide summarizes where and how to apply the chloride concentration or the chloride attack boundary condition, because there are several mechanisms how the chloride can get to the concrete. Typically the highest chloride concentration is applied at the top surfaces, where especially if you are from the regions with let's say tough winter, the de-icing agents used for the road maintenance in the winter season are based on some chloride containing chemicals and in the salts. So that's why the chloride concentration is usually the highest at the top surface. However, some spillage can go on also from the bottom and left and right side, as well as in some cases it needs to account for some potential emergency scenarios, which may be some leak through the drainage, or leak to the duct of the prestressing cables shown in here, and leak from the drainage system shown in here, or for example leak of the chlorides from the under the road finish, and then it can directly penetrate to the load bearing structure. Basically, the chloride ingress has several main factors. One is based from the material point of view. It depends on let's say how good is your concrete, because the better the concrete, the lower the diffusivity of the concrete. So, and also the type of cement is important to know, because for example some addition of the supplementary cementitious materials results in better resistivity of the concrete to the chloride attack. And then of course it depends on your exposure condition, meaning the temperature on site and the location of the structure. Also, it depends on the nature of the corrosion. If how well it is localized. For example, the corrosion due to the chloride attack is more localized, has a higher pitting factor than the corrosion from the carbonation of the concrete cover, etc. So this was the basic overview, and now I will just quickly go through the theory. So firstly, in the induction period, we calculate the diffusion problem with the time-dependent diffusion coefficient, and once the concentration of the chloride concentration at the position of the reinforcement exceeds some critical value, we move to the propagation phase in here, and in this phase we calculate how much of the reinforcement cross-section is corroded, and after it exceeds some critical value, it means that there is a possibility of the spalling of the concrete cover, and after that we assume that the corrosion continues under direct exposure at the atmosphere. So this is the phase from the cracking of the concrete cover to the spalling, and eventually it can lead to even the collapse of the structure if no contra measures are taken. When you do the pre-processing of such a problem in ATENA, I previously mentioned multiple parameters of the chloride ingress model. However, to be able to guess or assume them based on the engineering properties, there is this window in GID. So if you want to generate if you use the chloride attack boundary condition, or as we call it, chloride for surface, you have this parameter generation window, parameter generation tab, where you input the basic parameter about your concrete mixture, about the exposure at the site, and about the, let's say, position of the reinforcement in the model, and clicking here to the generate button, the GID automatically generates the material properties for you. So in case of a model for where you also use the bond for the discrete reinforcement, you can use the option, or in such an analysis it calls for using this option for setting the bond strength of the reinforcement as a function of corrosion. In here, I show just the data from this paper, where they measure the bond strength at different corrosion levels, and also summarize the research that can be found in the literature, and came up with the following function, which firstly, up to some level, shows a plateau, because this phase is related just this phase is described by some minor swelling of the reinforcement, or minor buildup of the pressure around the reinforcement, and once this pressure exceeds the strength of the concrete, the microcracks form, and we can see the reduction. The reduction of the bond strength. So, for example, if you have this data available, or you have your own measurement from the lab, you can input these into GID, and then during the analysis, the bond strength will be automatically adjusted based on the level of corrosion. So now I would like to move to just a quick comment on the workflow of the durability analysis, because for those of you familiar with ATENA, you know that when we're modeling the problem, everything is calculated incrementally, and we can define a loading history for the structure. And when dealing with this kind of like a long-term performance problem, this should correspond to a realistic history of the structure. So here I have some typical load displacement diagram, which can be seen as some outcome of the analysis, showing the midspan deflection at the bridge and the total load applied on the bridge. This diagram shows several stages. So typically, such a problem will have several intervals. Probably we will start with application of the self-weight and prestressing. In this analysis, it corresponds to the load level approximately to 5 meganewtons. We can see that up to this moment the response of the structure is mainly elastic. And then if we apply the remaining dead loads for the structure, we see, which is the level approximately at this point, we see occurrence of the first cracks and reduction of the stiffness of the model. Then in this case, in interval 3, there were applied the life loads, the design life loads, which increase the load level up to this point. This was associated with development of more cracks and in the growth in their width. However, under this state, it's normally done the evaluation for the ultimate state, ultimate limit state. However, if we apply the degradation mechanism at this state, the crack width at this load level will be used for calculation of the chloride diffusion. In some cases, it might be let's say very some safe estimation. Let's say let's some conservative approach. However, it probably does not represent what happens in reality, because the degradation mechanism acts on a bridge on bridges at probably in the long term at much lower load levels. Probably a good guess for the load level when to apply the degradation mechanism is the self-weight and the dead loads. That's the state of the structure, which is when the at this state the structure is mostly loaded. So in this case we use interval number 4 for unloading. You can see that we unload to slightly different. That there is some remaining deformation as we are in the nonlinear analysis, and at this moment we apply the degradation mechanism in interval 5. This is represented with this segment on the load displacement diagram. where the midspan deflection increases at the constant load. Finally, the design life load are applied again, and in the interval number 7, the overloading of the structure is simulated to access the ultimate load-bearing capacity of the structure affected by the degradation mechanism. Now, before I move to showing some examples of the application, I would like to check the chat box and also show you something directly from the software. So let me see if we have any questions up till now, or if we will keep them for later. Oh, so there was somebody actually asking if that about the problems with audio, but I hope it's already solved. It was at the beginning of the webinar, so I hope everything is fine by now. And apart of that, there are no further questions. So let's come back later, and I will show something from the pre-processing in GID and for reviewing the results. So in here we are looking at a model of a quite simple bridge structure. It has two spans. The span is about 11 meters in this case, I think. And in here you can see the finite element mesh, including the substructure here, the concrete deck, and these volumes correspond to the position of the loading where we apply the localized load when simulating the overloading of the structure. As you can see, I have this is the summary of the interval in ATENA. I have several intervals defined in here, and in interval number 7, it corresponds to the chloride attack. It is applied in 20 load steps. So I enter the interval, and I would be interested in looking at the chloride boundary conditions. So what I was explaining before, you can find it in the condition window. It is condition used for surfaces, and in here we have carbonation for surface and chloride for surface. In here you can find all the parameters which are needed to be defined for the chloride attack, and simplified parameter generation tab where you can which can automatically generates the inputs for you based on some engineering parameters. In my case, I already have some this boundary condition applied on the model. So if I plot it, I can show it in here and select the option draw and colors. And now the surfaces with the chloride attack boundary condition are shown in green and red color. It means that there are two different boundary conditions, or the definition is different for the top surface and for the side and bottom surfaces. And the difference can be seen in here, because if I want to plot through here draw field colors, I can plot the chloride concentration at the surface. It is this CS parameter. So if I plot it, I can see that about 0.9% of chloride content is applied on the top surface, and some lower value is applied on the bottom surface. This can be also visible from here if I go to entities and click here for chlorides for surface. I get the condition as a text input with all the parameters separated by some symbols in a single line. In here, this may be the useful feature is to click on the condition and use this transfer button, and then GID automatically transfers this condition to this window. Okay. And in here, I can easily review what's defined. Maybe I would like to bring your attention to this output, which is the concrete cover. This is not used in any way for calculating for actual estimation of the chloride diffusion speed or reinforcement corrosion, but it's mainly a post-processing variable, which can be later used if you want to review the chloride content at some given depth under the concrete surface. You input it here, and then in the post-processor you can see how the chloride concentration develops at the depth given here. For the reinforcement, it's the depth is automatically calculated, and when the chloride concentration exceeds the critical value at the position of the reinforcement, the corrosion process is started. Another thing which I would like to emphasize is here under this activate total function, which is its name in here, it's called chlorides. This function gives the relationship between the calculation step and the time in the analysis. For example, if let's say that the chloride attack should last for 100 years from the step, and from 15 to 30. So this information is provided to ATENA using this function. It can be found in this data materials functions, and if I open it here, this is the function called chlorides, and here is the relationship. So actually, in this particular case, at step 75, the duration of the chloride is 0. That's the starting point, and at step 95, I have this time in seconds for 100 years, I think. To define the time here correctly, you should review the units used for your ATENA problem. In this case, we can check it through here, through data and data units, and for time we see that seconds are defined here. So this should be the units in in this function. When we go to the reinforcement, we can see that there are several reinforcements defined in the material definition. They are differentiated based on the diameter of the bar, and you can see that here I have the bar with bond, and I have activated the corrosion dependency. I generated the parameters automatically based on the FIB codes. So these FIB codes parameter can be further reduced by the function of corrosion. So this is a relative function which is used to multiply the bond strength at given corrosion degree. So plotting the function here, you can see that it resembles the function the function previously shown in the slides. Now I would like to switch to ATENA Studio. In here I have the same problem calculated, and let's just quickly go through the results. On this part of the window I show the LD diagram, and here you can see the stress in the reinforcement bar and the crack width at this load level. The cracks are, now we are at the load level of self-weight and dead loads. And if we move a little bit further and add the live loads, we can see that the crack width increases. We can see mainly the formation due to the negative bending moment at the middle support, but also in the midspan at the left span of the bridge, and we can see the increase of the stress. The cracks at this moment increased from approximately 0.1 millimeter up to the 0.3 millimeters. That's the maximum crack in the midspan here. Then in step number 75, we see the unloading, which will be associated with a decreasing of the deflection and partial closure of the mechanical cracks. So at this load level, the cracks decreased from those 0.3 millimeter back to approximately 0.17 millimeters. So approximately half of the width at the load level. Also, we can see some remaining deformation on the LD diagram if I use better the scale. So from this point we moved back in here. And now in 20 steps, so from step 75 to step 95, there is this long-term degradation. So we should observe increase in the deflection. Slightly it was visible. Let me increase the deformation, and it's different for the plots. And again the crack width increased. So from approximately 0.17 millimeters, now the maximum crack is exceeding 0.2 millimeters. And afterwards, in the remaining steps, there is this overloading phase to get the maximum load bearing capacity. So here now the scale is too less. Maybe I should go somewhere in here. So in here we can see the beginning of the yielding of the reinforcement in the midspan. We can see large cracks forming in this region. Now they are about 1.4 millimeters in this region, and the stress in the reinforcement exceeds the yielding point, which is here defined as 550 megapascals. So at this point, we are approximately at the we are approaching to the load bearing capacity. So this was just a quick overview of the post processing. We can even, if I don't want to show the cracks in here, I can show the chloride concentration. So in here the output chlorides. I can see how the concentration how is the concentration over the structure. We can see that the highest chloride content is above the middle support, because there were the highest chloride there were the higher chloride content and also the widest mechanical cracks, while at the bottom surface the chloride concentration is much less, mainly due to the lower chloride content at the boundary applied there. When talking about the reinforcement, we can similarly plot the degree of reinforcement corrosion. So if I switch here to reinforcement corrosion, I can see that some of the parts are quite corroded. This is the single bars in here. However, mainly it's below. Let me see the scale clearly. Mainly we see the green color, which is about 50% of the reinforcement corrosion, meaning the half of the cross section is gone at this moment due to the chloride attack. We are I think a little bit running out of time, so let me get quickly back to the presentation and just give you the last information, which can be how to evaluate how to evaluate the load bearing capacity based on the FIB code, as I promised at the beginning. So if you still have time, I can show you this. So this is actually one of the application of this approach. It is the Wonka bridge in Pardubice, Czech Republic. In this bridge has three span, the largest span in the middle of about 70 meters. The bridge was constructed in 1959, and it has both the normal reinforcement and also the prestressing tendons. Those prestressing tendons are both types: the bonded cables in the concrete and unbonded cables in the box girder. Before the actual analysis, there were conducted some bridge monitoring to calibrate the model and to validate its short-term behavior. This shows some output from the measurement, mainly as mainly the main output from the measurement used for the numerical analysis was the relationship between the load acting on the bridge and the strain it induces in the bridge's deck. So based on that, we validated the finite element numerical model and calibrated some of the inputs. And now we can see the overloading simulation of the bridge. In this case, if the load is applied in the midspan, it's transferred by the cables above the support, where the compression of the concrete in the shear region and also between the support and the deviators of the prestressing increases as the load increases, and finally the failure mechanism develops there as a crushing of concrete above the support. So if this evaluation is done for different durations.
Sorry, I am not seeing the screen.
Thank you for the. How long does it occur?
After the simulation, we are not.
After the simulation, okay. Thank you for the. So thank you for this comment. So again, I was talking about. Hope it's fine now. Can you see the screen?
Yes.
Okay, thank you. So let me quickly summarize it again. This shows the bridge, which has 3 segments, the largest 70 meters in the midspan, and as I was explaining, it has both bonded and unbonded prestressing cables. As I was explaining, there was some measurement conducted on the bridge in order to calibrate the model, and after that we validated that and calibrated some of the inputs, and the result was the finite element numerical model. And here, as I was explaining, this summarizes the failure mechanism at the peak load. If we increase the load in here, it is somehow transferred by the cables above this support and ends up in this deviator. And as the load increases, the forces in the deviator increases, and it results in increase of the compression stress between the deviator and the support below, which results in formation of the compressive region, and due to the combination of shear and compression, the concrete is subjected to crushing, and that's the mechanism at the peak load. When we say that the load bearing capacity of the bridge corresponds to the state when the concrete starts to crash, which according to the European standard Eurocode is approximately it's exactly 0.35% of compression of compressive strain. We can say that at this moment we have the maximum load bearing capacity. So this can be done for a different duration of the chloride attack. For example, we can We can calculate this for the structure which is unaffected by the chlorides, and then again for the structure which is affected by the chloride ingress for 25, 50, 100 or even more years. And based on that, we can deduce how the load-bearing capacity decreases over the time. In this image, it's shown on the load displacement diagram, where these two lines corresponds to the structure unaffected by the chlorides, and this reduced capacity is from the analysis where we assume 150 years of the chloride attack. Furthermore, you can see two different analyses run by two different colors. One is done with the mean material parameters, and the other one with characteristic material parameters. And similarly for the run with the chloride attack. The reason why we have these two analyses is that in this case we applied the ECOF method according to the FIB model code. This method is called this is the abbreviation for estimation of coefficient of variation method, which can be used for assessing the design load-bearing capacity according to the FIB code. So this analysis relies on assumption that the load-bearing capacity of a structure follows log normal distribution, and this log normal distribution can be described by two values. One is the mean load-bearing capacity, and one is the characteristic. So based on this, we can calculate the coefficient of variation, and using the sensitivity factor and the reliability index as defined in the FIB model code, the global resistance factor can be calculated, and based on that, we can get the design structure resistance. Furthermore, there is one more safety factor, which describes the model uncertainty, which depends on your software, and for example, can also depend on the failure mode. In case of ATENA, for all failure modes, it's 1.16. So using this approach, you can end up with the design structure resistance, and then, as for any other method, we need to check if this resistance is higher than the load at the ultimate limit state. So then similar thing was done for the other structure, but I think we are a little bit running out of time, so this can be we can leave it for the next time. And now, if you have any question, I will be very happy if we have some discussion, or you can write your question into the chat box. And
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.